Welcome back to the Race to Near Space. Today we're joined by Russ Vanderwerf, a self described stratospheric evangelist. And that's not a joke, it's actually in his title. Vanderwerf serves as Vice President and Chief Balloon Evangelist at Aerostar, a world leader in the design and manufacture of highly technical aerospace and defense solutions. For more than 65 years, Aerostar has been advancing the field of stratospheric ballooning and reimagining what balloons are capable of. As you'll hear in our conversation, Aerostar has had a hand in some of the most interesting uses of stratospheric balloons over the past half century, many of which you've probably never heard of, such as a military project that took Air Force pilots by balloon to the middle layers of the stratosphere and then cut them loose, or flying telescopes by balloon to look deep into space for NASA, or building an 800-foot in diameter balloon that can carry a Chevy Suburban to the stratosphere. Get ready to find a new respect for the humble balloon. Russ Vanderwerf, thanks so much for joining us on the Race to Near Space.
Yeah, it's great to be here. Thanks for having me.
So, Aerostar got its start in a pretty unlikely place, at General Mills in the 20th century. Tell me how a cereal company helped kick off a half decade of advances in stratospheric ballooning.
Yeah, so we have a fun origin story. So during the 40s, everybody was working on defense stuff, right? So the war was just winding down, and there was a lot of interest in technology development. We got a lot of technology today out of those efforts. And one of the things that was being done was the start of the space race, the start of the exploration of the upper atmosphere. So some folks at General Mills, who, as you mentioned, they're a flour company basically, but they got started into the defense business. They had an aeronautical research division, a number of engineers there, and several of those engineers were working on high altitude flight. And so, coming into the late 40s and into the 50s, General Mills was realigning back to kind of their core business and working on food production. And they were shutting these programs down. And a number of the engineers who were working those projects, who were pretty passionate about what was going on, still wanted to keep doing it. And so, actually, there were a couple of efforts that spun out of that. One of them was Raven, and four of the engineers came to Sioux Falls, South Dakota, scenic, lovely Sioux Falls, started Raven in 1956. So Raven was actually started doing stratospheric balloons, doing high altitude research for the government, and then grew into a lot of other businesses. And then eventually Raven Aerostar was created in the 80s, and now it's just Aerostar. But we're still doing it. We're still doing high altitude work that those guys got started on way back in the 50s.
Interesting. Yeah, I'd like to stay there in the 50s. So, what was some of that US government research that the initial founders were working on?
Yeah. So you got to remember some of the stuff that was being done in the aerospace world back in that time. So the space race was hot and heavy, right? We were starting to work on rockets and space capsules, and then aircraft, jet aircraft were being developed, right? So toward the end of the Second World War, we started development of jet aircraft, and really through the 50s and 60s, we created what the modern jet aircraft is today. And jet aircraft are capable of flying much higher and much faster than uh, traditional propeller type aircraft would have been flown in the 50 years of flight before that. So one of the things they were working on and worried about was what happens if something goes wrong during a space launch? What happens if an aircraft is cruising at 50,000 feet and something goes wrong? The pilot needs to eject. So one of the programs that came out of that was called Project Excelsior and then Project Manhigh. So they were working on parachute systems, right? So how do we recover a pilot in one of those situations? And a number of people worked on it, but probably the most notable one is a guy named Joe Kittinger. He was a test pilot for the Air Force, and he started working on Project Manhigh in the 50s. So what they would do is they would use these high altitude stratospheric balloons to lift this guy in basically an open cage up to extremely high altitudes. They finished it over 100,000 feet. So for some kind of perspective, aircraft typically cruise at maybe 30,000 feet. So you're talking, three times higher than a commercial airline flight. So he'd go up there, and when they got up to that altitude, he'd jump off, which takes it takes something, probably more courage than I'll ever have. And it'd never been done before, right? So these ideas for these parachutes and these eject systems and whether they would work, I mean, we didn't know, right? So pretty cool stories coming out of that. There was one test on one of the early parachute tests where he jumped off and the parachute actually snagged on his spacesuit and his body went into a spin. He spun up actually to 120 revolutions per minute and fell 60,000 feet through the air without a parachute open. And of course, he blacked out. When you're spinning that fast and falling that fast, you lose consciousness. And he was only saved by his reserve chute, which opened about a mile or about 5,000 feet above the ground, managed to wake up by being slowed down by his reserve chute, untangle himself, get out of the spin, and put in a safe landing, and went on to do more of these flights. So talk about courage. After that happens. So those are some of the cool things that we were doing, and it expanded from there, dropping space capsules and all kinds of things like testing cosmic ray impacts on humans and animals when they were flying. We just didn't know what the upper atmosphere was going to do to life. It just hadn't been done. So a lot of really cool stuff there.
Yeah, that's super interesting. We had Alan Eustace, who set the world altitude record for skydiving on the first episode of the Race to Near Space, and it's interesting to hear that this history of jumping out of the stratosphere goes back quite a ways.
Kittinger actually held the altitude record from I think 1960 up through 2012, and then some folks got interested more from the perspective of seeing what could be done than from the perspective of NASA or testing. So there was Felix Baumgartner and the Red Bull jump, and we actually built the balloon that did that. And then there was Alan Eustace. So those records have been broken, but this guy held it for an awfully long time. Really cool
Oh,
stuff.
interesting. I didn't realize you built the balloon for the Red Bull jump. Anything interesting you can share on that one?
Yeah, no, I mean, I think you guys did a really good job with the interview last time. Some of the challenges of figuring out how to both survive at those altitudes and then recover safely from those altitudes. But yeah, it was a very large balloon. I mean, we'll talk about some of the really big balloons we make, but it's pretty amazing what it takes to get to those altitudes and lift that much weight. Um, but yeah, that's something we're proud of. It's cool stuff, and we do have a long history in that. Although we're not in the manned flight business right now, there are still folks doing manned flight on high altitude balloons. So it's a legacy we're proud of.
So I want to get back to your work with the U.S. government and specifically NASA. I mean, Aerostar has been working with NASA since basically before NASA existed. Um, could you tell me just a bit about the work the company has done with NASA and then maybe some other government agencies over the years?
Yeah, certainly. I mean, we're excited about our continued partnership with NASA, and we're proud to have that legacy. We talked about the history and what happened back in the 40s and 50s, but it really doesn't end there. So we've been working with the US government and with NASA continuously throughout our 65 plus year history. And we still do build balloons for scientific research for NASA today. So scientific research is a key thing that NASA does with high altitude balloons. There's actually a balloon program office out of NASA's Wallops Island facility, and they do 5 to 10 large balloon tests every year for scientific research. One example of that, last year they did a telescope called SuperBit, and this telescope was lofted by the balloon up to 80,000 plus feet and collected similar imagery quality to the Hubble Space Telescope. So, I mean, obviously, Hubble has the advantage of being in space, but this has the advantage of another 40 years of technology development. And there's some really cool imagery. If you go search SuperBit, Super BIT on the internet, you can see that they took of deep space objects. It's studying the origin of the universe kind of stuff, which is really interesting stuff. They actually launch out of Wanaka, New Zealand, which is a really cool place, and then also out of McMurdo down in Antarctica. So they actually are doing launches right now from Antarctica with our balloons for scientific research. That telescope flew for 40 days and went around the Earth 5 times taking images, and then was recovered in Argentina. So that's an example of kind of the scientific research stuff that they do. Um, to this day, space equipment is being tested on balloons. So the newer space capsules that are being developed for the newer space program efforts have been tested, dropped from balloons to test their parachutes, where they actually loft the entire space capsule up to altitude and drop it so you can simulate reentry into the Earth's atmosphere. Those are some NASA things, but it's not just NASA. So we're also working with, for example, the US Geological Survey on detecting wildfires and supporting wildfire fighters. So we've developed some systems for the balloons where we can provide infrared imagery from altitude. And of course, when these fires are going on, They are flying aircraft and things above the fire to try to map the fire out. And that's how they know where the front of the fire is, so they can tell the firefighters on the ground where they need to work and warn them when things are coming their way. But those aircraft are working in a very congested airspace. There's water bombers, there's observation, there's parajumpers, and a lot of different things coming in and out. And it's dangerous, it's complicated. Also, the aircraft are low enough that they're subject to updraft and smoke and things from the fire. When we put a balloon over a fire at 70,000 feet, the fire and the smoke and the clouds, and frankly, all the weather is pretty much below us. We like to say, we get our heads above the clouds, not in the clouds, but out of them to the top side, right, with the balloons. So the wildfire fighting support is focused on two things. One is actually collecting infrared imagery to better map out the fires. But the second and actually most important piece of it is providing communication. So a lot of the areas where these firefighters are at, mountainous, dense forested regions, there isn't good cellular coverage. They're not going to like carry a Starlink terminal around on their back. They need to get access to communicate when they have trouble. They need real-time information, from instant command. And so they use the balloons and standard cell phones. We can provide LTE or cellular coverage from the phone down to the firefighter and then relay it back from the balloon to the base so that they can call in for help and things like that. So that's a pretty cool application. Other US government things we're looking into, we're starting to work with NOAA, or the National Oceanographic and Atmospheric Administration, on studying hurricanes. So part of predicting how hurricanes are going to hit and how severe they are is modeling the dynamics of the winds and the clouds moving around within them. And right now, they collect a lot of that data with the hurricane hunters who fly aircraft into the hurricanes. They collect radar data from the ground and sideways from these aircraft, and they put that into the model. But we're asking, what if we can get radar imagery from above the hurricane? And the thought that we can predict more accurately where the hurricane's going to go by improving those mathematical models. So those are just a few of the examples of things we do with the US government. And a lot of these things that I just referenced are in the last 5 years since we've really matured the balloon technology. So it isn't just history, it's ongoing. And frankly, I think there will be a lot of new things that we haven't even thought of today that this new technology is useful for.
Yeah, it's amazing just to hear you talk about the number of things that balloons are able to do. I want to talk just a bit about the balloon itself. I mean, as a flight vehicle, you mentioned planes earlier and airships. What are some distinct advantages of using balloons to operate in the stratosphere?
Yeah. So I guess first zooming out a little bit, what is a balloon good for? So a balloon is a flying platform, like an aircraft, like a satellite, but it's kind of a unique niche in between those two things. So it's much more cost effective than either of those platforms. It has some of the advantages as a satellite because the altitude is so high. So you can see and sense across a very wide area or provide communications or other coverage across a very wide area. Compared to a traditional aircraft, it's unmanned. It's very green. It's eco efficient, right? We fill these things with helium and we run them off solar power. There's no fuel burned or anything like that. It's persistent, and we'll talk about navigation, I think, in a little bit, but we can place it where we want to. And then it's also long duration. So, we've run balloon missions for hundreds of days. I think our record balloon flight is 312 days or something like that right now. So there aren't very many aircraft that can last that long. Of course, satellites do, but when you put up a satellite, you're kind of committed, right? Whatever's on that thing is up there. You can't really change it, modify it, improve it. Plus, you're subject to orbital dynamics. So you're going to be where you're going to be, and you can't control exactly where that is. It's based on the orbit of the satellite. So it's kind of a sweet spot in between aircraft and satellites. Some of the benefits of being at that altitude and having that persistence include, I mentioned sensing across a wide area. So one example of that, we just did a press release. We just did some work with Scepter Air and ExxonMobil, where we're trying to model and detect methane emissions from oil and gas facilities in the atmosphere. So we want to see what's the impact. So of course they have wide area infrastructure, right? So think half the state of Texas is covered by different processing equipment, extraction equipment for these natural resources, and they want to be able to quickly localize and fix any kind of leak. And methane leaks have been a key global warming contributor. It's been in the news a lot since the recent COP meetings. And so what we're able to do is provide a platform that stays on target over those facilities and senses across dozens of miles at a time, looking for those emissions with a hyperspectral camera. So that's one interesting example. Another one would be disaster response. So, for example, compared to a satellite, a balloon is very responsive, right? I can put this thing in the air with a couple hours' notice and 4 or 5 guys, and then it can fly there for weeks or months at a time. So, an example of that would be, after Hurricane Maria hit Puerto Rico in 2017, um, Google Project Loon, who we were working with and building balloons for, put a constellation of systems, I think 7 or 8 balloons at a time, over Puerto Rico to restore connectivity to those hard hit rural areas where the infrastructure for cellular comms and stuff had been knocked out. So think of disaster response, also could be monitoring for oil spills, surveying damage from a hurricane. These are things where the balloon has a unique element of being inexpensive, quick to get in the air, and able to stay on target for a long time.
Yeah, and that's one of the fascinating things to me. I mean, you think of balloons, maybe latex weather balloons that sort of go up into the high altitudes, but are meant to basically pop once they get there and come back down. Obviously, you're talking about something vastly different from that if you're flying it for almost a year. Can you talk to me a bit about how these stratospheric balloons are constructed and the sorts of advances that you all at Aerostar have made over the last few decades to make them last almost a year?
Yeah, I mean, I could, but if I told you, I'd have to kill you. So maybe that's no, no, certainly. I mean, these are not weather balloons, right? We say balloons, and people think of the movie Up. We're tying a bunch of party balloons together and lofting some crotchety old guy's house. It's not like that. So these balloons, the main balloon product that we're talking about for a lot of these missions is the Thunderhead system, and we mentioned a little bit about Project Loon. It's similar to the balloons we were flying. Selling to Google for that project. And so these balloons say 50 to 100 feet across. So it's a pretty big balloon. And we can lift several hundred pounds. They're not made of latex. So latex is a great way to make a simple balloon shape, but it does not have the durability to sustain flight for hundreds of days at a time in the atmosphere. So we've worked really hard over, well, really 65 plus years, but especially the last 20 years on duration. And there are a number of special things that go into that. And really, some of those are the enabling technologies that have made all this possible. So, one example would be the actual plastics that we use. This is polyethylene plastic. So, think it's thin, it's like a garbage bag. In fact, most garbage bags are made out of similar stuff. But of course, we're not using simple garbage bag plastic. There are special formulations. The balloon actually gets pieced together. If you look at our balloons on our website, you'll see they're kind of what we call pumpkin shaped. Those little ridges on the pumpkin are what we call gores. They're strips of plastic that get welded together. And how we put them together is really important. And that's really where a lot of the special sauce is and what we've refined building 3 or 4 thousand balloons over the last 20 years and gotten to a point of high reliability and long duration. Some of the other things that go into it are, the balloon itself is one thing, but the electronics are just as important. And so the advantage in machine learning, miniaturization of computers and processing, better battery technologies, which has been driven heavily by the green revolution, by electric cars, solar panel technology. These are all the things that have kind of come together to make this uniquely technologically feasible now.
So, Russ, you mentioned the Thunderhead balloons, which I think you said were 100 feet across. Obviously, latex weather balloons are much smaller. What's the variation in size? Like, how big are we talking when we're talking stratospheric balloons?
Yeah, so actually, from our perspective, even 100 foot across is a pretty small balloon. So we talked a little bit earlier about the NASA research programs, and we build a balloon for them. We call it a Big 60. It's 60 million cubic feet by volume. I mean, that's a number that doesn't mean much to people, but a couple of reference points. Um, it's about 800 feet across when it's fully inflated. So you could fit the Superdome inside the balloon when it's fully inflated. And we will lift 6,000 pounds up to 140,000 feet with those balloons. Actually, one of those balloons set the sustained balloon flight altitude record here about 5 years ago. So those balloons we make in a plant that, I mean, if you're going to make an 800-foot long balloon, you need an 800-foot long facility. So we have a special plant where we make those balloons. We use 22 plus acres of plastic material to make those balloons. So it's actually pretty crazy where this stuff can go when your goal is lift a lot of stuff really high. I mean, we're talking about putting your Suburban 20 miles up in the air, right?
Yeah, yeah, that's something to think about for sure. It's really fascinating, especially hearing you talk about the advancements that have gone into making these balloons. fly for such long durations of time. I'm curious, when a balloon gets to 300 days of life or potentially longer, how are you monitoring the health of the balloon and deciding when to bring it back to Earth? And then ultimately, how do you do that?
Yeah, so that's an interesting topic and actually a lot more complicated than you'd think it would be. So, as you start to stretch the lifetime of these systems out, what happens is parts and pieces very slowly degrade. So, things like battery life get lower. It's hard on electronics to be hot and cold, but also the envelope, the balloon envelope, the actual shell of the balloon, very, very slowly leaks helium. So, we've worked really, really hard to make that leak percentage and likelihood as low as possible. That's really our special sauce. But at the same time, nothing lasts forever. And so one of the really interesting technical challenges is actually figuring out how to predict the lifetime of the balloon. So there are a lot of factors that go into measuring the pressure inside the envelope. It's very affected by temperature, by altitude, by stratospheric weather, by heat that's reflected off the Earth. And so we've put a lot of work into sensing a lot of those factors, and we've built a statistical model. And what we can do is we can see the lifetime of the balloon slowly shrinking as the balloon gets older. So we're always monitoring that. When we're flying balloons in the air, we're working with the FAA or whatever regional airspace authority, just like an aircraft would. We're filing flight plans, we're keeping them up to date. And as we notice that the balloon's lifetime is getting lower, what we do is we intentionally navigate the balloon back to a safe landing zone and intentionally land it with coordination with the FAA or whoever. So what happens is as the pressure in the balloon keeps going down and we can predict how much life it has, we'll fly the balloon back to a large open space like a field, right? And we can predict the landing point of the balloon because we're always modeling all the winds from the stratosphere down to the ground in Thunderstorm, which is our command and control software. So the pilot will choose a landing zone using that software and navigate the balloon there. And when the flight is done, the balloon shell itself is a one time use. So we actually have a system on the balloon that rips a big hole in the side of the balloon and all the helium goes out. And from there, the balloon and the electronics package come down on parachutes to land at that predicted landing point, and we'll have a ground crew ready to meet it and pick it up from there.
Not unlike someone jumping from the balloon, except it's the balloon itself coming down.
Yeah, exactly. A lot of that parachute development, and that's another thing we have parachute engineers here, right? Like before I worked here, I didn't know parachute engineers were a thing, but it's really challenging to make something that works reliably at that altitude. So we've definitely learned a lot over multiple decades of testing those kinds of things.
That's great. Something you just mentioned that I think is worth touching on is wind currents and wind speeds and how you're constantly monitoring those. I know those are super important for balloon navigation, and you touched earlier about how that's a really important part of making stratospheric balloons useful for real world use cases. So, could you talk to me a bit about how navigation works and maybe some of the advancements that have gone into that over the last decade or so?
Yeah, absolutely. So I would say navigation and understanding of the winds is probably the single biggest thing that has changed in the last 20 years and enabled us to do a lot of what we're doing. So historically, people think of balloons as something you let go. Like you said, they go up, eventually they pop and they come down. And a lot of the early flights, even when we talked about, they started flying balloons in the 1930s, and then we got involved in the 40s and 50s and onward. It was mostly modeled that way. And a lot of the large research flights are still that way, where they'll release the balloon, they'll model where it's going to go, and then they'll send a crew out there and eventually they'll bring the balloon down and collect it. That's really interesting and useful for doing high altitude testing, but it isn't as useful if you're trying to hit a particular area with a particular effect, like that communications bubble for wildfires, for example, that we talked about earlier, or putting a methane sensor over an area where there might be leaks. So, what we've been able to develop and really started, back in about 2012, we started working with Project Loon on this. And what we learned in flying several thousand balloons over about a decade is in the stratosphere. So we're talking, 40, 50,000 feet and up. There's a lot more diversity in wind currents than we used to think. And when I say used to, I mean even 10 or 20 years ago. So That altitude is not something that had been studied a lot, right? There's probably 100 years humankind has into, you know, numerical weather modeling, but the bulk of that effort has gone into figuring out if it's going to rain tomorrow, right? That's what people care about. They don't really care what direction and speed the wind's going at 62,500 feet precisely. And what we've been able to do is take the data we're getting from those flights, and we've been able to extrapolate using machine learning algorithms weather patterns that are occurring in the winds that we wouldn't have predicted with the very coarse numerical models that we use to predict surface weather. So, what we can do is if we know what direction the wind is going at a certain altitude and what speed, we basically operate the balloon like a sailboat in 3 dimensions, right? We raise and lower the balloon to catch different wind currents to get us from point A to point B or stay there over a target area. And that's really the nut we've cracked that I think has opened all of this up to being useful for general applications that would have been used for aviation or satellites instead of just scientific testing.
And how accurate can you get? I'm just curious. Just sort of riding these wind currents, I imagine there's not always the most favorable one that you would like, but um, can you explain to me just how accurate it can ultimately be?
Yeah. So the interesting thing about it is, like a sailboat, we're subject to the winds that are out there. So different times a year in different parts of the earth, there are more variable winds or less variable winds available. So one of the things we do is we use historical data to model that out. So if somebody says they want to carry out a certain mission, say maybe it's providing communications at a certain place in the earth at a certain time of year, what we can do is we can model out how much what we'd call station seeking winds, how much ability to stay in an area we're going to have. And then we need to provide more balloons. So if there's less diverse winds, your orbits, if you will, imagine you're kind of sailing in a circle by changing altitudes, could get larger. And maybe you need more balloons to keep constant coverage over an area. So as far as accuracy goes, I mean, we launch balloons out of South Dakota and we'll fly them to a specific point on the other side of the world. But it is one of those things where you can't do that all the time to every place. And that part of knowing that pattern and how to know what we can do and can't do and where we need to launch from to get to a certain point, that's part of the magic of kind of the wind modeling side of what our engineering team does.
Interesting. Yeah, and I guess I hadn't thought about just adding more balloons. That kind of helps increase the chances that you're going to be able to be over a given place at a given time.
Right. So if you can predict that the winds are going to be more or less favorable, or even maybe look a week out into the future and say, we're going to have a shift, you can pre position balloons. So this is where, if you want more continuous coverage, the balloons work in a constellation. So maybe you've got a city that you're trying to provide communications to, and maybe you have 4 or 5 balloons in the area over that city. But you're also looking out into the future and saying, okay, there are some strong winds coming out of the west coming next week. What we can do is move some of those balloons out to the west in advance of that wind event and then have those balloons take over. So as the western winds come in, some of the balloons will be pushed out of the area, but different balloons can move in. And then it gets kind of complicated. It's like choreographing a ballet, right? We need to look at all those systems, think about where they're going to be a week into the future, and then plan routes to get new balloons back in as things are moving in and out. I come from more of the mathematics and the computer science background originally, and I mean it's really fascinating, I think, as a problem to try to model.
Yeah, that's super interesting. I mean, just hearing you talk, the breadth of things that Aerostar has done with these stratospheric balloons is pretty amazing. I mean, we've talked about skydiving, testing equipment for NASA, obviously communications, monitoring what's happening on Earth. Um, Looking forward, what are you most excited about balloons in the stratosphere being able to do for our planet?
I'm excited about all these things. If that didn't come through in the discussion, I'll be surprised. But one thing that I think is really interesting to think about, and I did a little TED talk here a few years ago, is one of the things we don't think about is we take for granted what satellites can do today. But we've seen more in the news about it the last couple of years. Solar radiation and solar storms are not constant, right? They're reaching a maximum right now where this radiation is blasting out at the Earth, and there is a chance that that kind of thing could take out some of the resources, some of the satellites and things that we currently have available. And so what can you do then? You can launch more satellites, but if a bunch of satellites that are doing something critical, like providing communication for emergency responders, get blasted out of the sky, we can put balloons up pretty quickly, thinking hours, right, to reconstitute some of that. And it might be kind of a silly thing to sound like, and it's probably a thing we don't worry about a lot. I know you're all looking for more things to worry about, but back in 1859, which was the strongest solar activity that's recorded since we did a lot of electronics, there was something called the Carrington event where these solar flares, the storms produced by them, hit the Earth, and people were like literally working telegraph keys, and they were blasted out of their chairs by electromagnetic radiation. So there is the real potential of that and other disaster response. And I think, at Aerostar, our little tagline or our motto is we connect, protect, and save lives, right? Like those kind of things are really motivating and exciting to work on, at least for me.
Yeah, well, let's hope that doesn't happen, but if it does, we'll be thankful
Absolutely.
that Aerostar's around to put some balloons in the air pretty quickly. Um, I wanna end here. It's funny to talk about balloons because 'cause they're such a sort of, humble invention that have been around for so long. I think all of us are very familiar with them, not for stratospheric use cases, but just day-to-day use cases. I guess I'm wondering in a world where innovation is often defined as something new and novel and bigger and better, what is it about the humble balloon that gives it such staying power in this race to near space?
Yeah, so I'll give you two answers, even though you asked for one. I mean, one is what we're doing today is not something that would have been able to be done 100 years ago. So the advances in plastic technology, solar technology, machine learning, battery technology, it's a confluence of things, right? It's something old, something new, and something blue. I'm not sure. But, we're taking multiple things that existed, pairing it with advances in technology to make something new. And it's always interesting for me to get to talk to people about balloons and they go, "Oh, you're not talking about something simple here, right? We have a large engineering team working a lot of disciplines to make this happen." So, I mean, I think one of the misconceptions is that it's an old technology, but I will also say the one thing that is true about it is that the idea has been around for a long time, and some of the pieces have been around for a long time. And really, the simplicity and the cost effectiveness of using a balloon as a lift vehicle, I think will always keep it around because, when you're talking about an application where reliability is key, where duration is key, other solutions to these problems have a lot of moving parts, a lot of complexity. They rely on a lot of advanced materials, and they'll probably be able to do different things than the balloons will be able to do as they keep maturing. The balloons are going to be around, they're going to keep getting better, but they'll always have that reliability and cost effectiveness of the actual lift vehicle of getting to these altitudes that I don't think anything will match.
Well, Russ Vanderwerf, this has been really fascinating. Thank you so much for joining us.
Yeah, it's been great to be here, and hopefully, this has been interesting to people. And always excited to talk about what we do. It's really cool stuff.